This is a tutorial on SpreadModelR, an app that allows you to model the spread of some disease, of a population of an invasive species, of some pollutant, and so on. Those are just examples. Now, I coded this app with modeling the spread of chronic wasting disease in mind, so this will be the example that I will be using throughout this tutorial. Modeling means two things. It means simulating the spread of the disease using known parameters, and B, actually estimating those parameters from observations. And you can do both with this app. This video is meant as a tutorial, as a step-by-step instruction on how to actually use this app. It is not really going to explain a lot of the theory and the math behind it. If you want to know more, there's a ton of help files in this app. There are a lot of papers linked and so on, so you can read that. And I'm still going to give a very quick introduction right now, and I'll be using this app for that. So for the moment, don't worry about all those buttons and sliders and so on. The graph is what is important for the moment. Let's first look at the main equation. This here is a partial differential equation that is called the reaction diffusion equation. You can see there is something, U, density or something like that. We'll come back to what exactly this is, that changes over time according to two things. One is diffusion and the other is a growth term. Let's look at those one after the other. Let's look at just diffusion for the moment. And this is what you see here in the app. Let's assume you have a drop of ink that you dropped on a piece of blotting paper. At first, the ink is at one spot, quite concentrated, quite dark, but over time, it kind of spreads out. It diffuses out, meaning it spreads further and further away, but the density where you dropped it becomes smaller and smaller because there's a finite amount of ink, if you will, that you dropped in there, and it just becomes more and more diluted and spreads out further and further. Now, if you let this run for an infinite amount of time, the whole surface will be covered with an equal density. So this was the diffusion part here. It's governed by parameter mu, which is the diffusion coefficient. The larger this coefficient is, the quicker everything spreads out. Let's look at the growth term now. You can see here the parameter lambda just multiplies the density, or in our analogy, the darkness or the intensity of the ink. So relatively in space, it will stay the same, just in absolute values, it will grow or shrink. Let's look at this in the graph here. Same starting situation, you have your drop of ink on the blotting paper, and now instead of spreading out, it will basically stay the same, but just become more intense. So the numbers here will increase, and we can look at that. You see the numbers increasing. The fact that it looks like it's spreading out is an artifact of the plotting method, because the density is non-zero everywhere. This is a Gaussian distribution. That means even though if it looks like it's zero here, it's not actually zero. So when it increases due to the growth term, it kind of looks like it's spreading out. That's just because of the cutoff of the plotting method. If you don't like the analogy of ink becoming more intense, you can think of it of density of some bacteria. They're not diffusing out, but they're reproducing and becoming more and more in those spots where they already were. So now that is growth and diffusion, but that's not the entire story, because we at the moment have the diffusion coefficient and the growth coefficient spatially constant. they don't vary in space. Now, the density does, obviously, we just saw that. It varies with the x and y coordinate, and it also varies over time, but those two parameters do not. Now, we can change that and make them spatially dependent. Now, mu, the diffusion coefficient, depends on the location, and so does the growth coefficient. How does that look visually? We start with a similar situation here, but now imagine that the blotting paper is kind of different down here. There's a patch that is different, and in this patch, the ink diffuses more quickly. Let's look how this would look like. See, it looks a bit similar, but now you can see where the patch is, and it diffuses more quickly there. So the whole blob is not circular anymore. And it becomes elongated, goes in that direction. There's also still a growth term in there. This is why this becomes so incredibly large, because there's still a growth term, not just diffusion. And this is what this looks like in the end. So diffusion is not the same everywhere, but there are spots where it can be faster. Just to make it clear, diffusion happens faster in this area, but that means that in this area itself, there is less density because it diffuses through that area quickly and then slowly again on the other side. So up to now we have this analogy with the ink or bacteria, but how exactly does that relate to the spread of a disease like CWD in deer? The darkness of the dye or the intensity of the dye in our analogy is not exactly the prevalence, but it is some continuous measure of disease presence. What exactly that means is not really clear. It is not a direct biological analogy. This continuous measure of disease presence, this is shaped by both like host movement and local disease dynamics. Now, neither the diffusion nor the reaction term correspond directly to a specific aspect of disease spread, but together they allow us to model the combined effects of local processes like transmission or recovery. That happens primarily through the reaction term, or effects like host movement, which is captured primarily through the diffusion term, but not exclusively. There are other things that come into play. How the disease is detected, reproduction of deer. So it's not only the disease that gets transmitted, but the host might reproduce as well. And all this combined is in that reaction diffusion equation. So having large diffusion or small growth and so on might give you a bit of an idea on how the disease spreads, but there is no direct biological counterpart. Like we said, diffusion and growth does not have to be the same everywhere in space, but it can vary. Right here, we have an example of a discretely varying covariate, like this rectangle here, but that does not have to be the case. You could have it varying continuously over space, or you could have like patches like you have here. In our chronic wasting disease case, a continuously varying spatial covariate that could be elevation, forest cover, and so on, and a discretely varying covariate that could be a hunting area, that could be state boundaries, and so on. Probably something man-made, but could be something natural as well, just discretely varying in contrast to continuously varying. How this actually goes into the equation is actually quite simple. The diffusion coefficient is just an exponentiated linear combination of covariates, of spatially varying covariates weighted by parameters. The same for the growth term, spatially varying covariates weighted by parameters. A linear combination of those gives you the growth term. The reason why the growth term is just a linear combination and the diffusion coefficient is the exponentiated linear combination, that is just because we need the diffusion coefficient to be positive or non-negative. For biological reasons, for mathematical, for computational reasons, that's why we just exponentiated to make sure that whatever parameters or spatial covariates we have here, the diffusion coefficient is non-negative. As a side note, because before we talked about discrete and continuous and so on, the diffusion equation describes how the density, or we said the presence of the disease, varies continuously in space and time. But that is not how we solve the equation. There is an analytical solver, and that is even implemented in the app, but for the most part we solve this equation numerically. That means we discretize space into a grid. You can see that here in the app. We can, slightly see the grid here everywhere. And we also discretize time. So you saw that here with the slider. We don't calculate the intensity or the density at every time, at every point in time, but at discrete time points, time steps that I'll show you here. This is going to get more clear when I actually explain how the app works, just as a side note. So now we have this varying density, this presence of disease, or the way it is called in the publications that this app is based on, the spatiotemporal effect. This is what I will refer to from now on. You see it here, the spatiotemporal effect. That is not something we can measure. We said that. What we can measure in the field is observations in certain grid cells at certain times. Is a deer CWD positive or is it negative? This is the observation we can make. So we need a connection here. The connection is quite simple. The spatiotemporal effect that you see plotted here varies between 0 and infinity. We need a probability in every grid cell. So every grid cell needs to be a number between 0 and 1 that gives you the probability of encountering the disease in this grid cell at this particular time. Mathematically, this looks like this. You have the spatiotemporal effect U here, and that goes into a link function G that just squishes the domain that was originally for U from 0 to infinity to 0 to 1 for P, the probability. Now this is also the place where you can enter individual level covariates. So let's say you have an observation of a deer, location xi, yi at time ti, and that deer maybe has a certain age or sex given by vi. And there's also a parameter beta for those different covariates. Again, like it could be again a linear combination as we had it before. This multiplied with the spatiotemporal effect gives you a number between 0 and infinity again, because we exponentiated this here. So no matter what value of beta we have or what value the individual level covariate might take, this is always between 0 and infinity, and then gets squished to a number between 0 and 1, which is then the probability of encountering the disease in a harvested deer at location xi, yi at time ti. For the moment, let's assume that individual level covariates have no influence on the spread, on the diffusion or on the growth. So all betas are 0. Then this would look like this in the graph. Let's not calculate the probability here because those values are insanely high. The probability is just going to be 1 basically everywhere. Let's take a value here and switch from spatiotemporal effect to probability. So we'll squish it. There is not a lot of squishing because the values are already quite low, between 0 and 0.06. So it just scaled it. Nothing happened, it just scaled it. The spread did not change at all. So now we know we can go from the spatial temporal effect to the probability of encountering the disease in a certain location at a certain time, and from that then simulate a measurement, meaning a harvested deer that is either positive or negative. Obviously, we can also go in the other direction, collect measurements in the field, and then with those measurements, estimate the parameters that govern the diffusion and the growth in our reaction diffusion equation. That's basically it for theory. At any point, if you wonder about mathematical background, wonder about what's going on, you can always click on one of those green question marks. That opens a new modal window with a lot of theory right in there, a lot of math. You recognize this is what we already talked about here. There are a ton of different documents. Every tab of the app has different help files and so on. In general, up here, there are further readings, meaning the papers on which this app is based. And there's a document that I wrote up a couple years ago about the connection between diffusion equations and random walks. This goes a bit in the direction of what we talked about before. The spread of the disease in reality is not really something continuous, is not really a diffusion, because deer are not continuous, right? Deer are discrete entities, and they mechanistically probably behave more like an agent-based model. But there is a connection between random walkers, so it could be deer, infected deer that walk over a landscape, meet each other, transmit the disease, get infected, and so on. There's a connection between that and diffusion equations. That is written up here. In case you're interested, check it out. Also, you can always access the video, which you probably know because this is probably the way you already accessed it, the video of the tutorial you're watching right now. So, but that's it for theory. Let's reset everything and dive right into the app itself. Okay, here we are. And you see the app has several tabs up here. On the first tab, you'll just set the grid on which everything is based. Then there's two tabs to specify covariates. There's a tab to specify the starting distribution of the spatio-temporal effect at time 0, if you will, like the location of introduction of the disease, the parameters that govern the diffusion and growth, and then you can simulate the spread with those parameters, or you set up an Bayesian estimation of the parameters from observations and then run this estimation. You can extract the result, meaning the posterior distributions of the parameters from the MCMC estimation. Or you can analyze the results of different simulations and compare them. Like, how does the spread differ between different setups, between different covariates, and so on. Here you can download covariates that you generated, upload covariates, access help files and tutorials and so on, or just reset the app to the initial state. Just to demonstrate how the app works, we're not actually going to use real life data, but instead we're going to just arbitrarily choose some parameter values, run a simulation, and then generate fake observations, if you will, from those simulations. We'll then take those observations that we generated and estimate the parameters from those simulations, and probably, hopefully, we're going to get back the parameters that we started with. This is just for demonstration purposes. Obviously, you would not really do that in real life. You'd have actual data that you estimate the parameters from and then use those parameters to run a simulation. All right, but this tab here, the grid tab, this determines the entire grid. Right now we have a 40 by 40 grid with grid cells with a width of 1 and a height of 1. Actually, you see here, once I hover over fields, there's also helpful tooltips You can turn them off right here, hide tooltips. That's what we're going to do right now. The grid, as we have specified it now, is quadratic. It's 40 by 40 grid, 1 by 1 cells. Doesn't have to be that way. You could have a 40 by 45 cell grid. Right? You could have a different cell width, different cell height. Let's make the cell height 2, and that changes it. Now it's 80 high, 40 wide. Oh, 90 high, I'm sorry, 40 wide. Everything else in the app kind of depends on the grid, meaning that if you change the grid, or let me put it a different way, it doesn't make sense to have one covariate on one type of grid and another covariate on another type of grid, or to extract parameters that you obtain from a simulation on one grid to use them with a different grid. So that means once you change anything here in terms of number of columns or cell width, height, and so on, the entire app is reset. So you have to start fresh. So keep that in mind. When you change something here, everything you've done before is reset and deleted. Be careful here. Obviously, when you go from a 10 by 10 grid to 100 times 100 grid, you have 100 times more grid cells. But there are things here in the app that in the worst case scale O of n squared with the number of grid cells, meaning if you increase the number of columns and rows both tenfold, you might actually reduce the speed of the computations 10 to the 4-fold, meaning 10,000 times slower. So be careful with the number of columns and rows that you use. I've used up to 1,000 times 1,000 columns and rows, but everything gets really slow. This is on a laptop, caveat, but depending on your computer, just try it out. It might crash for really large grids. So now let's look at the setting up of the first covariate, which is going to be a continuous covariate. Let's go here. And this is the currently generated covariate. So you can generate covariates and you can upload covariates that you already have. Because we have a irregular grid or a rectangular grid, like I said, 90 by 40, this here is squished. To be quadratic, you can change the aspect ratio to the actual aspect ratio like this with this button. Let's go back, and actually for demo, you can do that with all graphs in the entire app, by the way, change the aspect ratio. But for demonstration purposes, actually let's use a quadratic grid. That just makes it easier for visualization. Doesn't change anything per se, but let's make it 40 by 40, 1 by 1. All right. So back here, new covariate generated. What goes on here in the background is called a Gaussian process. That does not really matter if you don't want it to matter. So you can just use this ruggedness slider to create a more or less rugged or smooth surface. So right now it's really rugged. Let's make it really smooth. Looks like this, right? A smoother surface. You can go really smooth. Don't worry about this warning here. I'll explain later what that means. But you can just generate surfaces like this. If you like the setting, this level of ruggedness, but you want a different instance of a surface, just click refresh. You get a different surface. Down here, you have the parameters that were used to generate this instance of a Gaussian random field. You have the covariance function, the sill, the range, the nugget, and so on. If that doesn't tell you anything and you don't know what that means, don't worry about it. You can just use the ruggedness slider, change the surfaces to your liking. If you do know what that means and you want to change it precisely, there's the advanced button. I'm going to come to that in a second, what that does. But before, what we have here is a continuously varying covariate. Actually, no, we don't, because we have a grid, right? Everything is based on a grid. It's a continuously generated covariate that is then discretized and put on a grid. This is true for the entire app. Everything is grid-based. But this continuously varying covariate that could represent habitat, elevation, average rainfall, something like that. Maybe you want a covariate that is kind of continuously varying, but cannot take any value between 0 and 1, but has like 3 categories, for example, 2 categories. For example, forest, open grassland, and wetlands, whatever. So you can discretize this continuously generated covariate by clicking the discrete slider like this. So now we converted it to something with 2 levels, or you can have 3 levels, and so on. So now you kind of have a discretely varying covariate, but generated from a continuous underlying process. For the moment, let's switch that back to the non-discretized version. If you want to download this covariate that you generated here, you can do so. You can click here. Those buttons are for downloading. You can click on this one to download a PNG image of the generated covariate, or you can click on that button here that will download the raster file of this covariate that you then can use in R. You can also click here, and this will actually generate the code with some explanations, generate the code that was used to actually produce this instance of a Gaussian random field, and actually precisely this instance. So the parameters that were used are already entered here. So if you copy paste this code in R, you get exactly this surface, and then you can play with it, change it, and so on. You can save the code by clicking here. Let's close it. By the way, these buttons are there throughout the app in all tabs. You can always click them to download an image, a raster, or the entire code. Maybe you don't want to generate a covariate, but upload one, a real-world covariate. You can do this here. You go to Upload Continuous Covariate Raster, click this, and now we're going to select, let's use Habitat. All right. So this is the uploaded covariate, and now all the sliders and buttons are gone because obviously you don't know how this, well, it was not generated. So you can't change anything with the sliders. It's just a real world uploaded covariate. The format of the covariate needs to be the same format as the ones you downloaded are in. So if you want to know how exactly that format looks, download just some covariate, open the file in R, and check out what's in there. It needs to be an RData or an RDS file that contains an object from the raster package, either a raster layer or a raster stack or a raster brick. So it does not have to be just one covariate. It can be multiple covariates because you can have multiple continuous covariates here. In fact, when we check this out, you see that there is a second covariate. Before we had continuous 1, it's still there, but we added another covariate, which is called Habitat, the one we uploaded. You can have more covariates, and you can do that down here. Let's use one that's called Forest. Add it. And now there's a new covariate in our group here called Forest. And you can do with that whatever, probably discrete 2 layers. So forest, not forest. You can always delete covariates again. So let's delete the forest covariate, and it's gone. This is our original first covariate, and there is the uploaded habitat covariate as well. Now, I said that there are advanced options as well. Let's check them out here. You can choose a covariance function, spherical, exponential, Maten. You can change the range, so how quickly the correlation decays. You can add a nugget, basically add an error. And you can change the SIL, so the overall variance. There is also an option to normalize it. That means it just generates a surface so that all values lie between 0 and 1. And it adapts the SIL accordingly. So when I click that, right now the SIL is 1. When I click that, all values are now between 0 and 1, and the CIL was set to 0.0224. Here you can set the method with which the random field is generated. You basically have two options, FFT or Cholesky decomposition. Cholesky decomposition is a bit more robust, but it's slower, a lot slower. So that decomposes the covariance matrix into a lower triangular matrix and uses that to generate the field. If that fails, it automatically falls back to eigenvalue decomposition. The FFT, that is a lot more efficient for larger grids, and it uses the FFT algorithm to convolve white noise with a covariance function in the frequency domain. The FFT needs periodic boundary conditions, so this is why you need to expand the grid to get rid of edge effects. Especially when you have a large range value, this might fail and the covariance matrix might not be positive definite. In that case, you can increase the expansion factor, or there's also a way to cheat. Use the FFT forced 0, and what this does is it basically just sets any value of the transformed covariance matrix that is negative to 0. So this is mathematically not correct, but if you don't care and you just want a surface, this is like a dirty workaround to do this. The ruggedness slider that we had when we're not using the advanced setup, that basically uses the FFT and never the forced 0 FFT. That uses the FFT. If it fails, it increases the expansion factor, and if that fails, it uses the Cholesky decomposition. It doesn't use the forced 0 FFT. But if you want to use that in the advanced tab, you can do this. Once you've generated an instance of a random field with a certain setup, the FFT of the covariance matrix is stored, so when you click refresh, it uses that and a lot faster to generate new surfaces. So generating a surface with a new setup might be a bit slow for very large grids, but when you click refresh, it's fast because it reuses the Fourier transform. If you want to know more about this, as always, there's the question mark, and there is a ton of help on how the Cholesky decomposition works, how the FFT works, what's going on in the background, and so on and so on. So that's it for the continuously varying covariates. You can also upload or generate discretely varying covariates. Let's click here. As before, you could upload a real-life covariate. Just upload discov, and it will go here into the group. Or you can generate one. Now, generating in this case does not mean using sliders because it's a discrete covariate. It actually means drawing. So you enter the value that the covariate should have that you're currently drawing, and then you can basically just drag a rectangle here and it adds this covariate. Now this is the value 1. Maybe I want another area where the value of this covariate, the discrete 1 covariate, where the value is 15. Draw it here. All right, now the value here is 15. The value here is 1. If you set the value to 0, you can basically draw holes in the covariate as well. You can always undo what you did. Clicking the undo button or redo. You can also use hotkeys, pressing U for undo or pressing R for redo. You can reset everything by clicking here. Now everything's gone and we can start fresh. There's not only the option to drag a rectangle, you can also freehand draw a polygon. Just one click somewhere, another click, and so on like this. You can draw a polygon. Once you're done, double click, and it closes the polygon. So this is the way you can draw discrete covariates. Especially for larger grids with a lot of grid cells, it might be hard to see, so you have the option to zoom in. Switch here from draw mode to zoom mode, or press Z on the keyboard, or D for draw. And now by dragging, you can zoom into this area right here. Double click zooms out again, and single click just zooms in a little bit and keeps the aspect ratio. Exactly as before, if you want to download a PNG of what you generated, you can click here. If you want to download the raster of what you generated, click here. That displays the code that will give you exactly this image. To add a new covariate, enter the name here, press add. To delete the current covariate, click delete. So now we have our covariates. We have two continuously varying covariates. We have one discrete covariate. What we need now is the starting distribution. The starting distribution is the value of the spatiotemporal effect at time 0, or at step 0. You can set that by placing Gaussian distributions on the map. So you select the location, click it, and that puts the center of a Gaussian distribution at that cell. Now there are two parameters. One is the dispersion. Increase that. And dispersion is basically the variance of that Gaussian distribution. And then there's the weight, which does not really matter right now because we only have one distribution. But we can place a second one. Let's put one right here. Now there's a second Gaussian distribution. Now the first one looks almost gone because the peak here of the second one is so high because the variance is really low compared to that one. So let's decrease the weight of the second distribution just to make the first one a bit more visible, just for visualization purposes, and maybe increase the dispersion of the second one a bit. Now, let's leave it like that. So now we have two distributions, two Gaussian distributions that together, the sum of them makes up the initial value of the starting distribution, the initial value of the spatiotemporal effect. As you know from the introduction, there is a link between the spatiotemporal effect and the probability at each cell of encountering the disease. And actually with this button here, we can switch between those two pictures. Right now we have the spatiotemporal effect, U. You can click this button here, and now we plot the probability of actually encountering the disease in those cells. To calculate this probability, we need the individual level covariates and the corresponding parameters. We set those in the parameters tab. So there's a link between the parameters tab and the starting tab. We're gonna wait until we've actually set those parameters in this tab here, and then we're gonna come back to the starting tab, and I'm gonna talk about how the probability is plotted, what exactly that is. For now, let's switch back to the spatiotemporal effect picture. So these here are actually our first 3 or 6 parameters that govern the simulation, or that can be estimated with the Bayesian procedure that I'm going to show you later. We have 2 locations, we have 2 dispersions, and we have 2 weights. Those are 6 parameters that govern the starting distribution and through that the simulation. So just to reiterate, what we have here is the spatiotemporal effect, or the quote-unquote distribution of the disease at time 0, so at that time when the simulation starts. We could have instead used a different picture and used the time since introduction instead of the dispersion as a parameter. So for example, we could have said we have 2 locations of introduction, 1 and 2, and the introduction at location 1 happened before the introduction at location 2. Let's say, for example, that happened 8 days before the simulation starts, so at time -8, if you will, and that happened 2 days before the simulation starts at time -2. Because at this location, the disease is more distributed already than it is here. This assumes, obviously, and the other picture with the dispersion as well, that from the time of introduction until the time the simulation starts, the disease has spread according to a homogeneous, so not spatially varying dispersion coefficient. So the disease has spread out from the starting location, regardless of the underlying covariates. And now at time 0, those covariates start having an effect because maybe up to time 0 we have no knowledge of what is going on with the disease. At time 0 we have this picture. How that happened, who knows, doesn't really matter, it's just parameters. At time 0 we have this picture, and now the simulation starts. Finally, there's this button here, normalize to PDF. If you click that, it just scales the weight so that the sum is 1. That makes this here a probability density function. Now, that is not necessary. The spatial temporal effect is in fact not a probability distribution. It can be made into something that is like a probability distribution function by scaling the weights. If you don't know why you would use that, just forget about it. If you need it, you'll know, you can click it. If not, do not worry about it. It's not important at all. All right. Yeah, lastly, obviously you can also remove parts of the distribution by clicking the X. That removes the stuff. There's the help files as usual. You can download a picture, the raster, or the code that generates this plot. So now that we set the first parameters, we can set the rest of them in the parameters tab. In the first section of this tab, you have a table containing all the non-zero parameter values for motility and growth. Motility, by the way, that is just a different word for diffusion coefficient in this context here. If you want to change parameter values or enter new parameters, you can click here. And now you see you have the option to enter a parameter value for the intercept, each covariate, and each interaction, both for the motility and the growth. Just as a reminder, the motility rate or diffusion coefficient, the spatially dependent diffusion coefficient, is just a linear combination of the spatial covariates together with the corresponding parameter values exponentiated. And similarly, the growth rate is just the linear combination of the covariate values with the corresponding growth parameters and an intercept. Right now, what is plotted here is the motility rate, spatially dependent motility rate. We can switch that here and also plot the growth rate. As usual, you can download a PNG of this plot or save a raster or generate the code that gives you this plot or that is actually running in the background to calculate the growth rate and the motility rate. Some explanation there as well. And if you wish to do so, you can download the code here and copy it and alter it as you wish. Finally, the last set of parameters are the ones corresponding to the individual level covariates, such as sex or age, for example. You can set them here. We do not have any values for those individual level covariates because they would be recorded with actual observations, and we've not uploaded any observations yet because we going at it kind of backwards and first doing the simulation and then actually getting observations from those simulations, estimating parameters and seeing if we get the original parameters back. Remember, in a real world setup, you'd have observations, estimate parameters from those observations, and then with those parameters run simulations, change some covariates, tweak some parameters to see what happens. So you'd actually know the individual level covariates. In that case, you could click here on empirical and you would draw values from the non-parametric empirical distributions of the individual level covariates that you uploaded. Like I said, we've not uploaded any covariates yet, so when we click here, we get an error. Instead, we can choose to draw just one covariate value and use just one beta parameter and draw that covariate value from a normal distribution, a uniform distribution, or keep it just constant to a certain value. And here you can set the parameters of those distributions. For constant, there is something else. I'll come to that in a second. For now, let's just use a normal distribution. What we want to do is this. We have the spatiotemporal effect. We get that from the starting distribution, the starting value of the spatiotemporal effect, which we then evolve with the motility and the growth that we specified just right now. And then we multiply this with the exponentiated linear combination of the individual level covariates, put that in the link function to transform it from a value between 0 and infinity to a value between 0 and 1, which gives us the probability in a particular cell to encounter the disease or not. And with that probability, well, that's just our Bernoulli distribution, and we can generate an observation that is either 1 or 0, positive for a disease, or negative. And we actually want to do that for every cell because we're just simulating, and simulating is free. So we can actually simulate an observation for every cell at every time step. So we need an individual level covariate value for every cell at every time step. And that value we can either draw from the empirical distribution of the actual individual level covariates, or like I just said here, we can draw it from a normal distribution. Or in fact, from a uniform distribution, or we can keep it at a constant value of 1, the individual level covariate. So now that we've set an individual level covariate and the corresponding parameter, we can go back to the starting tab, and now we can actually understand what effect this button here has. When we push this button, we draw a covariate value from the distribution we specified in the parameters tab for each cell here in the grid. And with that individual level covariate value and the parameter, the beta parameter we specified here, right? With those two things, we then can convert this spatiotemporal effect at time 0 to the probabilities at time 0, the probabilities in each cell, for each cell to encounter the disease there. So let's do that. Let's switch over to the probability. Looks like that. Now obviously that depends on the distribution here and the beta parameter. For example, let's make it really simple. If I switch to constant, then the individual level covariate value is just 1, which then means, with the beta parameter of 5, let's say, which then means if I go over here, the probability is just a scaled version of the spatiotemporal effect, nothing else. However, when I use, for example, a normal distribution, go back here, then obviously I'm bringing in some variation because in some cells the spatiotemporal effect is multiplied with a larger number drawn from the normal distribution or with a smaller number, and you can see this here. If we set the distribution of the individual level covariates to constant, meaning there's just one individual level covariate and it's always 1 in every cell, then there's a direct connection between beta and the expected prevalence. Let's go back here. This is the probability in every cell to encounter the disease. And in fact, the prevalence is the average over all cells of the probabilities to observe a case at a certain cell. So one determines the other. Beta determines the prevalence, and the prevalence determines beta if the individual level covariate is just 1. And this means that in this tab, you can specify either of those values. You can specify the prevalence. Of course, this is the prevalence at time 0, before the simulation starts. When the simulation is running, the prevalence will obviously change. But this is just the prevalence in the first step, or the 0th step, if you will. So you can either enter a beta value here, let's change it to 4, and this changes the prevalence, or you can change the prevalence, let's give a prevalence of 0.1. This gives you the corresponding beta parameter. This is probably a bit less useful when you're using real-life data, when you have individual level covariate values associated with your observations, but it might come in handy when you're just playing around with parameters, when you're running some simulations, trying things out, and you might want to have a certain prevalence in the first step. Now let's see what's going on down here. Those are the parameters that govern how the simulation is run. To understand what's going on here, let's very quickly talk about the computational background of the simulation. Remember, what we want to solve is the partial differential equation here. And we want to find out what u, the spatiotemporal effect, is at any time t and at any location x, y. Turns out that is not analytically solvable, or that has not been analytically solved so far. So we need to numerically approximate this. And we do this, the simplest way to do this is to approximate the differentials with differences. And there are several ways to do this. The simplest way is with the forward time central space approximation. And that's also what the algorithm is called, the FCTS algorithm. We've already discretized space because we have this grid, and that makes sense because the observations are probably also going to be recorded on a grid. Now we need to discretize time as well. So instead of calculating the spatiotemporal effect at any time t, we just calculate it after certain time steps. So let's say, for example, after 1 day, after 2 days, after 3 days, and so on. How does that exactly work? Let's look into the help files actually. Yeah, here. That's how to calculate the propagator matrix of the FCTS algorithm. That sounds and looks really complicated, but it actually isn't. It's quite simple. What this says is just you have the spatiotemporal effect at a certain time, and now you calculate it at a time that is delta t later. To do that, let's look at just one cell. At this cell, a time delta t later, the density, the spatiotemporal effect, is going to be smaller according to the diffusion term. That means the larger the diffusion coefficient, the more density is going to diffuse out of the cell. The larger the time step, meaning the longer the diffusion runs for, the more is going to diffuse out of the cell. And the larger the distance from the cell to the next cell into which the density is diffusing, the less is going to diffuse out. The further it has to diffuse in that time, the less density is actually going to diffuse out. And there's the growth term. The higher the growth rate and the longer the time step, the more the density is going to increase or decrease if the growth term is negative. Where does the density go? It goes to the neighboring cells, to the 4 nearest neighbors. And it also comes into this cell from the 4 nearest neighbors. Right? We're looking at one particular cell. The density in that cell decreases because it moves out of the cell, but there's also density coming in from the 4 neighbors. And this is according to those terms here. Again, the larger the time step, the more density is coming in from the neighbors. And the smaller the distance, the more density is coming in from the neighbors. That's basically it. That's the whole algorithm. You take a cell, you say density is diffusing out of that cell to the 4 nearest neighbors, and density is diffusing into that cell from the 4 nearest neighbors, and there's growth as well. So you do that for one time step, you have the new density, you calculate this for all cells. And then with those new density values at all those cells, you calculate the next time step. And that's the whole algorithm. That's it. Obviously, the shorter the time step, the more closely you're going to approximate the solution of the actual partial differential equation. Also, the smaller the distances between the cells, meaning the finer the grid, the more closely you're going to approximate the partial differential equation. But the grid is probably given by the setup in the field or the actual study setup. So now you kind of understand what the parameters are down here. This is just the time per step, meaning how long a step is. And this is just for how many number of steps you want to run the simulation. You might wonder what the units of time are down here, and that depends on what the units of this grid are. If we go from meters to kilometers here, then we'd have to increase the unit of time by 1,000,000 to get the same picture. Also, it depends on the units or on the scale of the parameters up here, the motility, the diffusion, and the growth rate. If the motility and growth are increased, then the time per step has to be decreased to get the same change per step. This is because we're doing a simulation. If we're actually fitting or estimating parameters from observations, then obviously the scale of the grid is given. This is just the grid on which we performed our observations. The time per step will also be given. This is just the time difference between our observations. And then the only thing left is the scale of the parameters, which we actually estimate. So this freedom here, this ambiguity between time and scale here and the scale of these parameters here, this is just because we're doing a simulation. In the case of observations and estimating parameters from them, this ambiguity vanishes. Finally, down here with this numerical input, you can tell the app how many steps to actually save. Because if you do a lot of steps and you have large grids, this will take up a lot of memory. You do have to calculate the spatiotemporal effect at every step because you need the spatiotemporal effect at the previous step to calculate it for the next step, but you don't have to save it at every step. You will have noticed that there's two inputs that I've not yet talked about. They're labeled advanced. Also, there's two plots labeled advanced. Long story very short, this thing here can increase the speed of the simulation, but it can also influence the accuracy. You can play around with that value, check for the sensitivity and so on, or you just leave it at a rather smallish value. And just don't touch this thing here. That story, a bit more detail, a bit longer. When you calculate the spatiotemporal effect at every time step, at every cell, that can become computationally quite inefficient, especially for large grid cells. So we can use a technique called homogenization to speed things up. We assume that diffusion and growth depends on two different spatial scales. One scale that varies very quickly over short distances, that would be, the vegetation type and so on, or the soil, and another scale that varies over large distances, geography, or some large scale landscape features. So what you do then is you scale up the grid cells by a certain factor. Now in this case it's a factor of 2, so you increase the height and the width of the grid cells by a factor of 2, so the area by a factor of 4. And then you calculate some sort of mean of the motility and the growth in those larger scale cells, mean of the motility and growth of the finer scale cells that will fall within this larger scale cell. Then you run the simulation on this larger scale grid. And then once you're done mathematically, you kind of put the fine scale variation back in. I'm being very hand wavy here and very vague because it's mathematically not that simple. If you want more details, you find them in the help files as usual. Especially here on the Simulate tab, there's extensive background on the simulation procedures. That is the homogenization procedure described here, the different algorithms and so on. There's extensive help here. And if you want to know more about homogenization, there's the main paper that describes it. Would be in further reading. It's this one here. It's this paper here. Look at this. That describes the procedure in quite some detail. How accurate the whole homogenization procedure is depends on several things. For example, when the dispersal distances are large relative to the spatial heterogeneity scale. So if the landscape, the original landscape, varies very quickly, and the disease spreads very quickly over that landscape, then it kind of averages out. The small scale variability kind of averages out, goes away. So using a coarser mean in the cells introduces little extra error. So a lot of small scale variation and large dispersion would be good for accuracy. Now, that's not something you can tune. The disease spreads the way it spreads, and the landscape is the way it is. So you see that is inherent in the system, the accuracy of the homogenization procedure. Also, when you do an estimation procedure, you don't know a priori what the dispersion is going to be. So you don't know how accurate homogenization is going to be and what homogenization scale is still possible to use. You want to use a large homogenization scale to speed up the simulation, but not too large so you lose accuracy. Like there's some values in the literature, for example, for like a normal CWD survey, it's recommended to have a scale factor of about 10. Yeah, look up stuff in the literature or just do some sensitivity analysis. Or if you want to be on the safe side, just keep it lower. Just to show you what it looks like, the homogeneous version of the growth rate would look like this. So you have cells that are with 4 times the area and some form of the mean of the fine scale growth rate in those cells. Same for the motility rate. And there's one last input in this tab, and that is to select the algorithm. There are 3 different options here. One is CN, that stands for Crank-Nicholson. The other, I already mentioned that one, stands for forward time central space. And the last one is an analytical approach. Between the 2 numerical algorithms, I'd recommend using the CN, the Crank-Nicholson algorithm. The difference between the 2 is that the FTCS algorithm moves forward in time using only information from the current step, while the Crank-Nicholson algorithm uses information from both the current step and the next step and averages them. That makes it more accurate. In fact, it's second order in both space and time. Doesn't really matter. But it makes it also more time consuming to compute with. In each step, you have to solve a system of equations, while in the FTCS algorithm, you don't have to do that. However, it is also unconditionally stable, and that's quite important because the FTCS algorithm is only conditionally stable. That means if time steps are too large or certain parameters are chosen wrongly, and wrongly means so that the propagator matrix has negative elements. If that is the case, then the whole thing becomes unstable. The simulation will run, you will get a result, it's just not worth anything. It's completely wrong. It's not just a little bit wrong, a little bit inaccurate, it's complete garbage. So when you select FTCS here, you get a warning. The smallest element of the propagator matrix is negative. That means the time step is too large, or the parameters are too large, lead to a negative element in the propagator matrix. So what you can do now, if you want to use FTCS and not Crank-Nicholson, because again, with Crank-Nicholson, you don't have that problem. If you do want to use FTCS, you need to make the time step smaller. So let's set it to 0.1. And now you see the smallest element of the propagator matrix is now not negative anymore. It's in fact positive. To make sure that you know what parameter values you can actually choose, you can click here, Show Limits. And this will calculate the parameter limits within which you must choose the parameters so that the propagator matrix has no negative elements. Calculating this does take a bit of time, so only do it if you really need it. Almost done. There you go. Okay, so now we know as long as, with those parameter values here, as long as the time step is smaller than 0.342, the propagator matrix will only have positive elements. Those limits are also calculated for the parameters. We can go here and you see all the limits printed here. So for example, the parameter for the continuous, for the variable continuous 1, for the covariate continuous 1 must be between those two values. The intercept must be smaller than this, given all the other parameter values. So given all the other parameter values, this value must be smaller than this. You note that the calculation failed in some cases. This happens when you have a lot of covariates. And right now we do have a few, so the calculations might fail. You can switch some parameters, slightly change them, run the calculation again, then it might work. It's an optimization procedure going on in the background, and that might fail, but with a different start to the optimization procedure, it might work. So it's worth changing parameters just slightly and then run it again. Also, you note we changed the algorithm, so the prevalence is actually changed because it is calculated after running the simulation for one step. Then it is calculated what the prevalence is given this beta parameter. So if you change the algorithm, the prevalence will also slightly change. And lastly, we can switch the algorithm to analytical. Now you can calculate the spatiotemporal effect at any time t and at any location. So there are no time steps. That's why they're gone. You can calculate it at any time. Sounds great, but there's a big drawback in that there must be an assumption made for there to be an analytical solution, and the assumption is that the motility, the diffusion, is locally constant. That is a very strong assumption. That means the results from a simulation running with an analytical approach will be quite inaccurate compared to the numerical approaches that I showed you. But the calculation is basically instantaneous. So if you just want to try out some simulations, or you have very large grids and you just want to get a feel for the parameters, that would be a way to do it. First run some analytical simulations, and once you get a feel for the system, you can then switch to one of the numerical solvers. Also, be careful that the analytical approach works with a starting distribution on the coarse grid scale. Remember the homogenized grid scale, right? This means that the starting distribution here will not be the same for the analytical approach and for the two numerical approaches. So there's also no way to mathematically convert the two starting distributions into each other. So keep that in mind when running the simulation. Now, let's switch back to Crank-Nicholson and actually run a simulation. By the way, before we do that, again, let me just one more time remind you of the help files. In those help files here, there is a lot on instabilities of the FTCS algorithm. And if you want to know more about the algorithms and how they work, you find that in the help files of the Simulate tab. That's the next tab. All right. So now let's set some reasonable parameter values. Let's set the time step to 1. Let's keep 20 steps. Let's keep every step. Let's reduce that to 4, let's say. And actually, let's not use a constant distribution. Let's use a normal distribution with a standard deviation of 1, or actually not 1. Let's use slightly lower standard deviations so that there's not so much influence, or there's not so much variance in the individual level covariates, so that you still can see very clearly what's going on with the diffusion process itself. So let's use 0.5. And let's switch to the motility rate. See what's going on here. The motility is really high up here and basically 0 everywhere else. That's not going to make for an interesting simulation, so let's switch up some parameters. Let's keep the intercept, but let's reduce the continuous 1 covariate, because I remember that one had quite high values up here. So if we reduce it, then that shouldn't be as extreme. That looks a bit more reasonable. See here on the scale. And maybe with the discrete 3 covariate, let's give that maybe 0.1. All right. That was the discrete covariate where we drew the patch down here, and maybe add some habitat, 0.3. Okay. Load. Or actually, you know what? Let's make the habitat a bit more extreme, 1.5. Alrighty. So, yeah, that looks good. I'm happy with that. Let's close it, and let's change the growth parameter. Do we want to have interactions? No, let's leave the interactions to just make it a bit more clear what's going on. Let's leave the interactions for now. But now we want to add some growth parameters. So let's switch to the growth rate plot so we see what's going on while entering the parameters. And now let's enter the growth parameters. I'm going to leave the intercept and the continuous 1 covariate. Let's give that negative growth. Why not? Let's give that minus 0.5. That was too much. Minus 0.05. All right, better. So now we have negative growth up here because that is where this covariate, the continuous 1 covariate, had high values, and positive growth down here because that is where the covariate had negative values. All right, then the discrete covariate, let's actually set that to 0. So the patch we drew has no influence on the growth. We're gonna compare that then later to a simulation where the discrete covariate has a lot of influence on growth and motility. For now, let's leave it, but let's give the habitat a certain value, 0.01. Okay. All set, I think. So now with those parameters, we have our growth rate defined and our motility rate and all the simulation specific parameters and the parameters that determine how the individual level covariates are generated, because we've not uploaded any observations and have to generate them. Let's go to the Simulate tab to actually run the simulations. Let's run the simulation. That should only take about a second or so. Because we have a very small grid and only a few time steps, and didn't take long. Here you see the spatiotemporal effect, or the time evolution of the spatiotemporal effect for all 20 steps. If you want to plot fewer steps, you can select what steps you're plotting here. Let's say we plot all the steps between 5 and 15. That's them here. Or you could just plot them individually, every single step, and then you can scroll through them and see how the spatiotemporal effect evolves. You saw that we started here and here, the two parts of the starting distribution, and it kind of moved more towards that direction. That is because the motility here is actually very large. That means density diffuses out of here quickly, and the motility here is lower, so it tends to accumulate there. Also, the growth term was positive here and was negative here. If you check the growth rate, positive here, negative here, and the motility rate was large here, so stuff diffuses out of here and accumulates in this area, and this is exactly what you tend to see in the simulation. So that was the spatiotemporal effect, but you can also plot other things, for example, the probability. Remember, the probability is just the spatiotemporal effect multiplied by the exponentiated individual level covariate values and a parameter. The individual level covariate values at each cell and each time step. And we simulated those from the normal distribution with a standard deviation of 0.5. So let's see what that looks like. It kind of follows the general shape of the spatiotemporal effect, of course, but there is a lot of variation that came in through the variation of the individual level covariate. Forgot to say, of course, there's the link function as well. So the spatiotemporal effect multiplied with the individual level covariate is then put into a link function that transfers it from a scale between 0 and infinity. As you can see here, it's not between 0 and infinity, but it could be, to a scale between 0 and 1. So the highest value here is a probability of 1, of course, and the lowest value is a probability of 0. The probability at each cell, at a particular cell, to encounter a case, to encounter the disease. From that probability, you can, of course, also calculate the actual observation using just a Bernoulli distribution. So let's switch it so you can see it better. Let's take this step number 1, of course, so we can go cell by cell. And with the probability value at that cell, we draw an observation. So with a probability of, well, this cell here, that's about 0.7. With a probability of 0.7 here, you have a case, and with a probability of 0.3, you have no case. Or in this case here, you're definitely going to have a case because that's about 1. Let's do that. Plot the sample. That's what it looks. Those are the samples. If you want to plot the covariates in addition to the samples, so you see better what's going on, you can do that by clicking here. That adds the continuous covariate. And you can also add the discrete covariate like this. If you want to switch what covariate is actually plotted, you need to go to the covariate tab. Right now, continuous 1 is selected. You can switch to habitat 1. Go back here, and it has changed to habitat 1. Of course, both covariates were used in the simulation. This is just which one is plotted. Same works if you switch to this view, and you see how the observations evolved over time. The observations and the probability are directly calculated from the spatiotemporal effect. That means if you want to draw a different set of samples, you don't have to recalculate the spatiotemporal effect. So if you click Run Simulation again, it doesn't run the entire simulation again, it just draws a new set of observations. So that goes really fast. Now we have a different set of observations and a different one. All right. The same is actually true for the probability. Because to get the probability, we need to draw from our distribution or assumed distribution of the individual level covariates. So again, we can select probability, click here, and it just draws new values for the individual level covariate. So it gives you a new set of probabilities without recalculating the spatiotemporal effect. So drawing new set of probabilities, drawing new set of samples, doesn't need recalculations, just click, gives you a new draw. This simulation was run with a Crank-Nicholson algorithm, but like we said, there's other algorithms as well. If we would have selected the FTCS algorithm, qualitatively, this picture would have looked the same. Oh, I forgot to mention, here's also the homogenized process that we can plot. So this is the evolution of the homogenized spatiotemporal effect on that large grid scale, on the coarse grid scale. But back again to the different algorithms. We could have used the FTCS algorithm, would have given us more or less the same picture. But when we use the analytical algorithm, the analytical approach, things are a bit different. So let's try that out. Let's go here, set this to analytical. And as you know, there's no time steps here. So when you go to simulate, there are no time steps that you can select, but you can select any time you'd like using a numeric input. Right now it says plot from time 1 to time 20 every unit of time, But you could say plot every 1.3 units of time, and it does that. And you could plot it from a time of 1.954 to a time, well, of 20, whatever. So anytime you can obtain the solution of this time evolution of the spatiotemporal effect. Same thing, of course, with the probability. Nothing changes here, or the sample, nothing changes here. Overlaying the covariates, and so on, nothing changes here. When you switch here to the single view, you can just enter any time you would like, 4.678. There it is. But remember, there are very strong assumptions underlying the analytical approach. In particular, the assumption that the motility, the diffusion rate, is locally constant, and that leads to a very different result than you would get with the numerical approaches. So just use that to get a rough overview of what parameters to use, what the parameters values could be, and so on. Now that we've run a simulation, we can also analyze it or compare it to other simulations. To do that, we need to store the results. So click here, and let's give it a name first. Let's call it analytical, and we'll store it. And let's store some others as well. So let's go back to the parameters tab, run the Crank-Nicholson algorithm again, run it, and make sure, yep, that looks about right. It's the same as before. Let's store that as well. Let's call it Crank-Nicholson, and we'll store it. Do notice that every time I change parameters here in the parameter tab, the current simulation is deleted and you have to run it again. Simulations are not stored in a buffer or something like that. That would take way too much memory. So every time you change parameters here, the simulation has to be rerun. So do store it if you want to keep the results. The exception are the beta parameters, of course, because like we said, the draw of the individual level covariates is completely independent of the spatiotemporal effect. So if you change beta here, it just updates the simulation. It just updates, well, not the spatiotemporal effect, it updates the probability and the sample. You don't have to recalculate it. And another thing, just to make sure that that's clear, this storing the simulation here stores the result of the simulation. Nothing else. If you want to store, well, basically the state of the app, meaning all the covariates, the starting distributions, the parameters that you entered, and so on, and then later on, even what you've entered here in the setup of the estimation procedure, you can store just the state of the app. So when you open the app and you upload a state file, it just gives you the same state of the app as you've left it. You can do that here, save current state, and then you can upload the current state again. This just saves all those parameters here. It actually does not save the stored simulations. It just saves the current simulation with all parameters. It saves it by downloading a file that you can send to someone else, that you can upload yourself, and so on. When you store the result of a simulation here, that is just to store it temporarily, to then use it in the analysis process. That is just to save memory. You cannot download those files. They only exist in a temporary storage. Once you close the app, they're gone. Just once again to reiterate, because when you run a long simulation, it's kind of annoying when everything's gone. If you want to store everything, do use this here, save current state, upload a state. Do not use this. This is just temporary to then use in the analysis. If you want to, of course, save a PNG, you can click here as usual, PNG of this here or of the single plot view. You can download the rasters. When you click here, this downloads a list of all the rasters, the spatial temporal effect, the probability, the sample, and so on. And of course, as usual, you can generate the code. That's the last way of actually storing results and downloading them, is to download the code that allows you to then completely recreate everything as usual with some explanations and so on and so on. And in the end, you get the same plot and the same rasters. If you want to know what exactly you've stored here, you can always click on the magnifying glass. Tells you all the parameters you used, shows you the covariates that you've used, the starting distribution, or the starting location. The parameters governing the starting distribution can be found here, just so you know what simulation is what in case you forgot what you named them. Before we analyze simulations, I'll actually add a third one, because so far we've only run simulations where the discrete covariate, so the patch that we drew more or less in this area, had very little effect. Let's see what effect this patch has when we increase the corresponding parameters and run a third simulation so we compare it with the other two. Let's go back to the parameters tab, open the parameters, and let's increase the influence of discrete 1 on the motility. Let's say we increase that to 1.2. Well, that might have been a bit too much. Let's say 0.8. Okay, better. And let's increase the growth to 0.05. Let's see what influence that has on the growth rate. A little bit, maybe increase it a bit, 0.1. All right, you can see that the patch here is a bit distinct. Okay, that's our third simulation. Let's run it. And just again, the simulation we've run before is gone. Clicking here does not bring it back. That just selects it for analysis later. It is not stored. Just the results are stored. You cannot bring them back here by clicking in this table. You would have had to download the state before, then you could have uploaded it now, but we didn't do that, so it's gone. Run it again. Now we got this simulation here, and you kind of clearly see the effect that the discrete covariate had. Well, there's a combination of high motility, so density diffuses through that area or out of that area quickly, but that's counteracted by the growth rate that increases the density in the area of the patch. Let's store that simulation as well, and let's call it CN/patch. Okay, so now we want to select the simulations that we want to analyze. This is just done to save memory, so now you actually bring them back from a temporary file to then use in the analysis tab. Let's start with those two. The Crank-Nicholson with the patch having a large effect, and the other Crank-Nicholson simulation. Let's select those two and hit select. Don't forget to hit select, otherwise they're not available. If you go to the analysis tab now, it says there's no simulation stored or no simulation selected. You need to first, click select. So let's do that. We selected them, and now they're available here. You see simulation 1, simulation 2. We've skipped those two. Those two tabs are to set up and to analyze the results of the estimation procedure. We've said we're going a different route than you probably would in real life. We're simulating first, generating observations from the simulations, and then estimating the parameters back from the observations generated from the simulation. So we skip those two tabs now and directly go to the analysis of our two simulations. I just realized something, and what I've realized is that the parameters of the simulations were not very intelligently chosen, because what we're analyzing here is all based on the probability. the probability of encountering the disease in each cell. And when you go back to the Simulate tab, the spatiotemporal effect, that looks just fine, but the probability is very low in parts. Now, obviously, in real life, we couldn't steer that. That's just the way it is. But now we want like a nice simulation for visualization purposes. So I think I'm going to change that. I'm going to go back to the Parameters tab, and instead of having large variation in the individual level covariate, I'm going to have small variation, set that to 0.1. The beta value just to 1, so the influence is not as large, and the probability was really kind of low everywhere. And remember, we multiply the spatiotemporal effect with the exponentiated individual level covariates and then put it into the link function. So the larger the individual level covariates, the higher the probability. And I'm gonna set the mean to 3. Again, this is just me tuning a bit so it looks visually appealing and we better see what's going on, just to explain the simulation and the app a bit better. In real life, obviously you shouldn't choose that. You should use whatever distribution corresponds to what you want to analyze or to reality. Right now we're just choosing it so it's more visually appealing. And like I said before, when we go to the Simulate tab, we don't have to run the simulation again. We've just changed how the probability is generated, so now this is the probability. It looks a lot more like the spatiotemporal effect because we've reduced the variance of the individual level covariate and the parameter. Good. So this is the CN patch simulation that we've updated. So let's delete the original one by clicking here. Call it again CN patch, and let's store it. We also need to do that for the CN simulation so the two are comparable. Let's look what parameters we used. We used alpha discrete, so that's the motility of the discrete, the motility parameter corresponding to the discrete 1 covariate, that was 0.1, and the growth parameter was 0. So let's do that. Discrete was 0.1 and growth was 0. Okay. Let's run that again. It's a probability, looks reasonable. Kind of similar to the spatiotemporal effect. And let's store it. Well, first delete this one so we can give it the same name. Delete this and let's call it CN. Store. Okay, now we want to select those two simulations and let's click select. And now we go to the analysis tab. Sorry for the confusion here, but this is just going to be a lot easier to see how the analysis works and what influence exactly the discrete covariate has on the spread of the disease. As I've said previously, we analyzed the spread of the disease for different simulations, mostly in terms of the time evolution of the probability. So the probability for every cell to encounter the disease there. In the first tab, you set up the analysis, and in the second tab, you actually carried out and look at the results. Now, spread is not a very well-defined concept, so we're going to come up with several different metrics to actually compare spread. Some of them are based on cutting off the probability at a certain value and then looking at the cells that have a probability higher than that cutoff value, and then look at, for example, the area they cover and so on. They're different metrics, but they're based on implementing a cutoff and looking at the cells with a probability higher than that cutoff. Now those cells are plotted here. There are no cells that have a probability higher than the cutoff of 0.4. That is the value we're currently using. So let's reduce the cutoff. I'm going to admit I've tried it before, what works well, and 3% is actually a cutoff that works quite well. So what you've plotted here is the first step of the simulation. Called CN, the Crank-Nicholson simulation where the discrete covariate had a very low parameter value. First step of the simulation, and the cells with a probability higher than 0.03 or 3% fall within the black borders here. We can augment that plot by also plotting the probability values by clicking here on probability. Now the probabilities are plotted as well, and all probabilities that are below the cutoff of 3%, they are on a grayscale here, and only here. Only the probabilities higher than the cutoff are on a color scale. The probabilities are not that high. All are lower than about 25%. So the color scale is not, doesn't display the full range here in the plot. So now we can look at the time evolution of those polygons. We can move the slider up here and display the polygon with the probability values higher than the cutoff for different steps. And of course, we can also do it for the other simulation, the CN patch simulation, where we had the a larger parameter for the discrete covariate. Oh, and by the way, in case that was not clear, the 2 points here that are marked S1 and S2, those are just the starting locations of the simulation, the ones we set in the starting tab of the app. All right, let's go back to the CN simulation and randomly select a step, let's say number 9. That's not the only thing we can plot here, the probability I mean. We can also look at the covariates. So let's instead plot the continuous covariate, and we can select which one. We're now plotting continuous 1, but there's also habitat. We can look at that as well. And we only have one discrete covariate, so there's nothing to select here, but we can also plot the discrete covariate in addition to that. Again, if you want, look at the time evolution. That's how the disease spreads across the landscape. Let's turn off the discrete covariate again, just for visualization, so you see better what I'm doing now, because there are different options of plotting the polygon. You can plot the border, that's what we're doing right now. You can just plot it filled, or inverse fill, so you only see the covariate values where the probability is higher than the cutoff. Or you can, turn off plotting completely. Let's go back to the border plotting. You probably have noticed that there are holes in the polygon right here. When we switch back to probability, those are just cells where the probability is lower than the cutoff, and they fall within the larger polygon shape. There's an option here, it says fill holes. When you click it, the holes are filled and they're gone. Now those areas belong to the polygon as well. If we don't have fill holes selected, the smooth option is not available. But if we fill the holes, then we can also smooth the polygon. Let me quickly show you what that looks like. This is what it does. Before, the polygon edge was very jagged because it just followed the outline of the grid cells very closely, and maybe you don't want that. Maybe in your application that doesn't make sense, so there's the option to smooth it. The smoothing is governed by 2 parameters. If you increase this one, it gets smoother, so to speak. Same when you increase this one. Set them both to 20. Okay, before I tell you what exactly is going on and how that algorithm works, this seems a bit arbitrary, right? You're just smoothing somehow the polygon and making it larger than the actual area of the grid cells that fall above the cutoff. It's totally fine as long as you do the same thing for all steps of the simulation and for all simulations. And actually this app doesn't allow you to do anything else. So whatever you use here, the parameters you use here will be used for both simulations, see? And for all steps of all those simulations. Let's go back to CN. And now let's talk about how this algorithm works. It starts with the unsmooth polygon, so let's turn off smoothing. And now you have the polygon unsmooth, but with filled holes. And to the polygon, it also count these areas up here. So the polygon consists of several patches that make up the entire polygon. The first thing the algorithm does is it represents the polygon boundary with a lot of single points. How many points are used? Well, that can be set here in the advanced section by the parameter polygon points per length. It's set to 5 now, and you probably can leave it at 5. That just means that per unit length, in this case that's exactly also the length and height, the width and height of a grid cell. Per unit length, there are 1, 2, 3, 4, 5 points used to represent the polygon boundary. Okay, and now the algorithm finds the convex hull around all those points. Convex means that there are no indentations. So this is definitely not a convex polygon because there are concave sections, there are indentations here. But when we actually show the convex polygon, it looks like this. So this is a convex shape, no indentations. And you can visualize that by imagining that the points representing the border are nails hammered into a board. And now you take a rubber band and you snap it around those nails. The rubber band is the convex hull of those nails. In other words, it's the smallest polygon that covers all points and is only convex. Okay, now if there is a convex hull, there must be also a concave hull, right? And there's actually many different concave hulls. The concave hull in our nail and rubber bands analogy will be obtained if you select a nail. And for example, let's use this one. Here is a nail that will be on the border of the original polygon right here. Let's use that as a nail. And now the polygon edge is pulled towards that nail, is pulled inside towards that nail, creating an indentation or a concave section. And then maybe you select another nail, let's say back here, and then you pull the rubber band in here. So we need an algorithm to select nails around which we get to pull the rubber band inside. And the algorithm works like this. It walks around the polygon border and looks at every edge. If an edge is shorter than a certain threshold value, it's skipped. That's the first parameter of the algorithm, the threshold. If the edge is longer than the threshold value, the algorithm will try and find a point to pull the edge in. That point will be the point that is closest to the edge, but inside the polygon, and does not lead to edges that cross over. The point must also fulfill a certain distance requirement. The distance requirement depends on the length of the edge that we're pulling in and on a second parameter of the algorithm, the concavity parameter, that one right here. Now, this is a bit counterintuitive, but the smaller the concavity parameter, the farther the edge is allowed to be pulled in. So the farther the point to which the edge is pulled can be from the edge. And like I said, it's a bit counterintuitive because it means the smaller the concavity parameter, the larger the indentation, or the larger the concavity, if you will. This is just convention. This is how it's used usually in this type of algorithm. So I just follow the convention here. just keep it in mind and don't get confused by it. So in summary, if you make this parameter smaller, you can build indentations from shorter and shorter edges. And if you make this parameter smaller, you can pull edges farther inside and make more pronounced indentations. All right, let's try this. The shortest polygon edge in the original polygon that you can have has a length of 1, because that is the width of our grid, or the height of our grid cells. So let's use a threshold of 2. And then let's see what happens if we reduce the concavity parameter, so allow for deeper and deeper indentations. Speed things up a bit, set it to 5. There you go. Okay, as you can see, it wraps more and more tightly around the original polygon shape. This was, of course, applied to every single step of the simulation, so you can look at the other steps as well. And of course, also to the steps of the other simulation. Okay. So that was polygons. And we'll see when we talk about the analysis itself, not the setup, what kind of metrics of spread we can look at or we can derive from those polygons. But there are other things from which we can derive metrics. One is points. For example, we can look at how far the disease has spread from certain points towards certain points and so on. There's already 2 points on the map. It's the starting locations, S1 and S2. You can add more points. You see the point button is selected. So that means you can draw points here on the map just by clicking somewhere. Let's click here. Another point was added, the point number 1. It's here, also added to the table with the coordinates of that point. If you want to delete it again, you can press the trash can symbol. You can actually also click on the table to highlight the corresponding points. And I think let's add another point, this time outside the polygon. Let's add it here to this cell, point number 2. These points are now defined for the CN simulation, but not for the other simulations. So when you switch simulations, the points are gone. Only the starting locations are there, which in this case are the same for both simulations. You could now draw or add points to the second simulation as well, or you can go back to the first simulation where you've already added the points and click all. Now that gives you a warning, because with all, you can transfer the added points to all the other simulations. But that deletes the already added points for that simulation. So now we click confirm, and the points 1 and 2 that we've just added are also now available in the CN patch simulation. Like I said, they're available in all steps. Let's go back to our CN simulation. There's something else we can calculate metrics from, and that's areas. We can go down here again and switch from points to areas. And now we can draw areas on the map similarly to what we could do in the discrete covariate tab group. And actually there already is a certain area available. That's the discrete covariate. You can click it, plots it here. But let's add more. Same as with the discrete covariate tab group, give it a name. Let's leave it at area 1, and then you can just draw on the map. You can add more shapes. You can draw polygons by single clicking and double clicking to close the polygon. You can switch between drawing and erasing using this switch here, or by pressing the D or E hotkeys, and now you can make holes into your area. The area shows up here in the table as well, and you can completely delete it by clicking the trash can, or you can undo or redo things you did by clicking those two buttons here. You can have multiple areas, or area types, if you will. Let's add another one, and let's just call it, well, let's call it area 2, whatever. Let's call it area 2, draw that. The eraser was active. It's called area 2. Draw it. Here it is. Bit more. Here it is. You can click on the areas in the plot, in the table, I mean. Click on area 1. It shows area 1. You can click on area 2. It shows area 2. The one that you clicked last is active, and you can add shapes to it. The one I clicked last was area 2, so I can add more shapes to area 2. If I deselect area 2, area 1 is active, and I can add shapes to area 1. So this is how you build areas. Maybe it's useful to also zoom in, and you can still do that, the same as in the discrete covariate tab. That's up here, the last button up here that we haven't covered. That switches between drawing and zooming. Click it. There's also a hotkey to do that. Press Z for zoom. And as before, single click, zooms in, double click, zooms out, and you can also draw an area into which it zooms. Double click to zoom out. I'll switch from zoom mode to draw mode again. And now I could do the same as we did with points. Click all and transfer the areas that I drew. Transfer all those areas to the CN patch simulation as well. I'm just gonna leave that. We're just gonna have areas or areas additional to the discrete covariate for the CN simulation, but not the CN patch simulation. Let's go back to looking at the points, and well, let's deselect the areas so they're not in the way. Let's go to points. There's another thing that we can look at and derive metrics of spread from, and that's headings. So with that, we can analyze things like in what direction does most of the spread happen, and so on. To do that, well, we can do that down here. Let me minimize that first so we have more space, because we don't need the polygons at the moment. Yeah, to do that, you need to select a point from which the headings are defined. You can do that here. All the points, the two you added, plus the original starting points are available. Let's just use start point number 1. It's the one up here. In case you forgot, you can click, it highlights it. But yeah, that's the one up here. And let's look at headings, or let's look at how the disease spreads in this general direction. So headings between 0 and 90, doesn't really matter. So heading between 0 and 90. Okay. Once you're happy with the values, you can add them to a table by clicking plus. And now they appear in a table. We have headings between 0 and 90, starting from start 1, so the starting location number 1. You could add more headings going off of this point or other points. Let's add another one, let's say from point 1 and in this general direction here. So let's say from 120 to 180. And let's add it to the table. If I select one of the rows of the table, it highlights the corresponding angles like this. That's the angle we selected. And there's the other one here. You can delete them by clicking the trash can. Something I forgot to show you is, let's select that again, is after you've put a set of headings on the map, you can then alter them. If you select the table, you can change the heading. It automatically adapts it. Okay, but now let's deselect the heading, deselect that point, and let me show you the last plot you can make on this tab of the app is the angular plot up here. The angular plot plots either the maximum or minimum distance from a certain point to the polygon edge for all headings. For example, for S2, the maximum distance to the polygon edge in this direction is obviously this. In this direction, it is this, not this. And in this direction, it is this, and so on. So this kind of says, what is the maximum distance the disease has spread from a point for all headings? You can also plot the minimum distance. That mostly makes sense for a point outside the polygon. It kind of says what is the closest the disease has gotten in that direction to that point. So in this case here, northern direction at 0, heading 0, that would be this distance here, not this distance. Let me show you that. Let's select S2. Okay. Let's go to the angular plot. So this is the maximum distance from S2 to the polygon edge. You can switch to the minimum distance by clicking here. I apologize that this is down here. I didn't find any room up here. Anyway, it's down here. You can switch between maximum and minimum. Like I said, minimum distance mostly makes sense for points outside the polygon. So let's look at point number 2. Click on angular and go to minimum distance. Obviously, for certain headings, there is no distance because, well, let's go back here. For all those headings, the distance to the polygon is infinity, so it's not plotted. When you plot the angular, oops, added a point by accident. Let's delete it. When you plot the distance, the angular distance from a certain point that also has headings, say number 1, let's use number 1 and show the angular plot. And then the headings are also displayed in this plot. All right, so that's it for the setup of the analysis. Let's actually carry out the analysis itself. Before you start the analysis, you can select for which steps you want to run it. If you don't choose to run it for all the steps and you later want to run it for the remaining steps, you don't have to run the entire thing again, just for the remaining steps. But now I think we'll run it for all steps we have. Let's run it and wait until it finishes. It might take a few seconds. All right, here we are. And now we have a lot of different metrics that we can plot. I'm going to go through each one of them. The first one is just the prevalence on the entire map for the 2 simulations. So you can select which simulation you want to show in the graph, or both. So you can see for the CN patch simulation, the prevalence is always higher than for the CN simulation, and it decreases a lot faster. You can plot either time or steps on the x-axis. In our case, it's exactly the same because we have a step length of 1. Switching between a time and step representation is of course a lot more important when you have simulations that have different time steps. But in our case, where the time step for both simulations is the same, it doesn't matter. All right, let's go to a different plot. That's the prevalence. We're in the prevalence group. That's the prevalence depending on the values of the continuous covariate. So you have all continuous covariates available, which in our case are 2 for both simulations. So the covariate continuous 1 and the covariate habitat for simulation CN patch and the simulation called CN. Let's just plot it. Let's compare the prevalence in the continuous habitat, the continuous 1 covariate. What it actually does is it shows the prevalence among all cells that fall between this and this value of the continuous 1 covariate for both simulations. The default of those two values is so that it covers the entire map. So this is actually exactly the same graph as we plotted before when we plotted the prevalence of the entire map. You can see that here. But of course you can reduce that and, for example, only look at the prevalence among cells that have a positive value for the continuous covariate called continuous 1. Now you have to add it first to the table. Click it. It's down here in the table. Here. For both covariates, we added this covariate value range. Well, let's look at it together with the other values. And wait, like this and like this. So we have the prevalence on the entire map in red and blue. And we have the prevalence only for continuous 1 covariate values between 0 and the maximum in green and in purple. Next, we can also look at the prevalence among cells that have a certain discrete covariate value. There is only one discrete covariate and it only has one value, and that's discrete 1, and the only value that takes in our simulations is 1. So yeah, we can just compare that. That is the prevalence inside the patch defined by the discrete 1 covariate for simulation called CN patch in red and CN in blue. And obviously that's no surprise. The prevalence for the simulation called CN patch is a lot higher in the actual patch than for the other simulation because we defined it that way. We said that the growth rate is a lot higher, or rather the growth rate parameter corresponding to the discrete 1 covariate is a lot higher in the CN patch simulation than it is in the CN simulation. Next, let's look at the prevalence in our user-defined areas. There are no areas defined for the CN patch simulation, but we have our area 1 and our area 2 that we defined for the CN simulation, the ones that we drew by hand. All right, and then there's not only prevalence that we can look at, metrics in terms of prevalence, but also in terms of area. The first one is the area covered by the polygon. Covered by the polygon that contains the cells with a probability that are higher than the cutoff, plus whatever we define in terms of smoothing of the polygon. In our case, I think if I remember correctly, we've used the smooth polygon. Yes, we did. So we have a very much smooth polygon, and it's the area of this polygon over time for both simulations. That is plotted here. Next, you can calculate the compactness of the polygon. The compactness is calculated as the ratio of the area of the polygon to the area of its convex hull. So that means the more jagged the polygon is, the smaller its compactness, and the more it resembles its convex hull, the larger the compactness. So this would be helpful to assess the shape of the disease spread. I mean, a more compact polygon indicates a concentrated spread, while a less compact polygon means a more dispersed spread, if you will. Then we can calculate the rate of change. So it's the rate of spread over time calculated as the change in the area of the polygon between consecutive steps. And I mean, that just tells you how quickly the disease is spreading over time. Next, we can look at the area between certain angles, between certain headings. We have no headings defined for the CN patch simulation, but for the CN simulation, we have two headings, one going from point number 1, user-defined point 1, and the other going from the starting location. Let's look at that, and let's look at that. So that lets you kind of assess the intensity of the disease in certain directions. Then we move from the area to distance metrics. First, the maximum distance to the edge. And this is called the average of the maximum distance to the edge. Remember when I explained what the angular plot does, I talked about how we look at the minimum or maximum, now it's the maximum, distance to the polygon edge from a certain point. And to find the maximum distance for certain headings, we separate the headings into bins. And this is actually how many bins we use is given by the n angles parameter. So we separate it into 100 bins. And for every bin, we calculate the maximum distance from the point to the polygon. The average over all bins of the maximum distance is what is plotted here. Let's do that just randomly for the starting locations. Then you can also plot the quantiles of the distribution over the bins. You can plot the quantiles of the distribution of the maximum distance to the edge over all bins. Now that sounds really complicated. You can do that and specify what quantile. Right now it's the median, but you can choose any quantile you want. And finally, there's the maximum distance direction. So this is, let me go back here. This is, we have plotted here the maximum distance over all headings. And now among those maximum distances, which one is the largest, so the overall maximum distance, and in what direction is that? In this case, I estimate it's this direction here. So this plots the direction. So this here is a heading. Plots the heading of the largest distance to the edge from that point. And you can also plot not only the highest value, the largest distance, but also the second and the third largest together with the largest, to give you kind of idea how variable the direction of maximum distance to the polygon edge is. So all those metrics, they kind of tell you what is the farthest extent the disease has spread in a specific direction, what is the direction in which the disease has spread the farthest from a specified point, and so on. The counterpart to that is the minimum distance, which mostly makes sense when you look at a point outside the polygon. We said that, so let's look at point number 2. And here we look at the average of the minimum distance. So kind of on average, how close has the disease come to that point? Same thing as with the maximum distance, we can look at the average over all bins, the quantile, and the minimum distance direction. So we can estimate that already from the plot probably. The minimum distance direction for point 2. Oh, that's actually the maximum distance. Let's switch to minimum. All right, so the minimum distance from point 2 at step 13 of the CN simulation, I'd say the minimum distance heading is this here, about 320. All right, let's see if that's actually correct. That would be 0.2 of the CN simulation, and at step 13 you're about at, well, 320, heading a 320, right? Same thing, you can compare different simulations, or you could compare different points for a same simulation or different simulations, whatever. The 2 lowest values, the 3 lowest values, and so on. Okay, then there's also distance to cells, and this is the last group. This is now not the distance to the polygon edge or the furthest distance or the closest distance or whatever. This is the distance from a point to every cell center, or to the center of every cell that lies within the polygon. So it is not necessarily every cell with a probability value higher than the cutoff, but if you've smoothed the polygon or filled holes, something different, it's the cells, all the cells that lie within the polygon, or at least the center of them is within the polygon, and it's the distance from a point to all those cell centers. And you can look at the average distance to all the cell centers, example start 1, or the quantile, certain quantile, for example the median. If you want to look at the minimum or maximum, remember the quantile 0 is the minimum, and the 1 quantile, the 100% quantile, that's the maximum. So with a quantile function you can also look at the minimum distance to all cell centers from the point, or the maximum distance. And this metric would help you compare, for example, central tendencies, or just the shape of the whole polygon. Of course, if you have the same polygon area, but your polygon is very elongated, looking from a certain point, then you're gonna have a higher average distance to all the cell centers than when your polygon is basically circular around a certain point. Those are all metrics. As usual, it's the same hint always. You can click the question mark. There's all metrics described, for what purpose you would use them, how to plot, and so on. By the way, now we've calculated the analysis for all steps, and we've plotted it for all steps. Without recalculating, you can reduce the steps for which it is plotted. No problem there. All right. The final thing to do is to look how the analysis would look like when you've run a simulation with an analytical algorithm, because then it's a little bit different. So for that, let's go back to the Simulate tab. Let's actually run a new simulation. Let's delete them all and run a new analytical simulation here, and let's store it, name it analytical. Let's run it from time 1 to time 12 with a time step of 0.5. Okay. Store it as analytical. Good. Now, if we click select, then all the stuff we've done in the analysis setup tab is gone, overwritten. But we don't care about it anymore, so we're just going to click select. And the analysis cannot on the fly calculate results from the simulation for different times. So this is the time, or these are the times that will be used for the analysis. So from time 1 to time 12 in steps of 0.5, this will be what is used for the analysis. If you want to do the analysis for different times, you have to store it as another simulation. Before, let's reduce the cutoff to 3%. Doesn't really matter. Let's not do anything else here. You can sample through the steps. It's 23 steps. Let's run the analysis very quickly. And let's just plot the prevalence. And now you see it makes actual sense to switch between steps and time. Steps you have 23. Time it is from 0 to 12, as we've put in here. All right, this is the peculiarity when you have an analytical simulation, and that is it for the analysis. Next, I'm gonna off-screen generate observations from our CN simulation. Right now, there's still the analytical simulation here, so we're gonna rerun the simulation with the Crank-Nicholson algorithm. To make it a bit easier to get observations from the simulation, or so that we get more observations from the simulation, I'll scale the individual level covariate a bit and give it a mean of 4. This just means that from the same spatiotemporal effect, all probabilities in every cell will just be a bit higher, and hence we have more positive observations, which then makes it easier, a bit easier to fit or estimate the parameters. I'm gonna keep everything like this, and we're just gonna generate only 20 steps, which is very few. That means you generate observations from 20 different days, if you will, and most surveys run a lot longer, but just to keep things short and to demonstrate stuff, we're gonna use just 20 steps. Okay, so let's run the simulation. Looks like before, you already know it. We can delete the analytical simulation. I will now download a raster containing all the observations that we generated in the simulation. Let's first look at them. Here they are. And let's switch to single view so I see it a bit better. For every cell, there's an observation. Most cells, the observation is negative. Some cells, the observation is positive. What I'm going to do now is take those observations, delete about, let's say, half of them, so it's still easy to estimate parameters, or it's easier to estimate parameters even though we only have 20 steps. But it's still a bit more realistic than having every observation, because in the field, I highly doubt that you have a field protocol where you record at every time step, every cell, or you have an actual observation in every cell at every step. In the case of chronic wasting disease, that would mean that at every time you harvest a deer in every cell and determine its CWD status. Highly unlikely. So we kind of sparse things out a bit and delete about 50% of all observations, positive or negative. I will download the raster or the rasters for every step 1, and I will do this off screen. So download the raster, and I'll be right back with the observations. Or actually, before I close the app to generate the observations, let me quickly save the state of the app so I can get back all these covariates, the starting distribution, the parameters, the simulations, and so on. I'll go here and click Save Current State. And I'll press Save and save it as CWD sim data. Yes, override it. And now I can close the app and come back to this later. I opened the CSV file for you where I put in the observations, and this is the format that you will also need to provide to the app to import your observations. The first column has the observations, negative or positive, -0, +1, here's a 1. The next column has the time, which in fact is a date. So we assume in this app that you can have at most 1 observation per cell per day. All right, so this has no hours or minutes or something like that, just the date. Next 2 columns are the X and Y coordinates of the centers of the cell where the observations were made. So you notice whatever system you have, spatial recording and so on, you'll need to convert it to this here. So you'll need to convert it to the grid that you specified in the first tab of the app. In our case, it was a 40 by 40 grid. Back then, it didn't have any units. Right now, it will have units because those are simulated, but they represent actual observations. So this could be kilometers from a certain 0 point, for example. Same with the time, of course. Now, one time step is a day. Before, it was just some arbitrary unit. With every observation, you record an individual level covariate. I just called it indivCov1. It's just a placeholder. It's just some random covariate. It is, in fact, that normal distribution, or the covariate generated from a normal distribution that we generated in the Simulate tab of the app. You could have more covariates, just add more columns with the corresponding covariate values. So those individual covariates, once again, they could represent sex or age or something like that. It can be just any number. It can be a factor. So if you enter a letter, A, B, C, and so on, the code will interpret it as factor and represent it in a dummy notation. And also, it will generate all the interactions of all individual level covariates. And you'll be able to fit parameters to the interactions as well. Now I'm going to show you how to import those observations into the app. Before we do that, the final thing, just to show you, we have here 16,000 observations, which makes sense because we had a 40 by 40 grid and we ran it for 20 steps and we deleted half of all the observations that we obtained in a simulation to get our real life quote unquote observations, 16,000 of them. So now I'm going to close that, open up the app again, and show you how to import it. And we're back. Obviously, the app is completely blank. Everything is gone. We're just with the normal startup state of the app. But as you remember, we saved our last state, so we can upload all the covariates that we will need to then run the estimation procedure. So it was saved under CWD sim data. So we're reading that in. That might take a second. Already done. So everything's here. Our two covariates, the continuous covariates, our discrete covariate, the starting distribution, the parameters from before, and our last simulation as we left the app. So everything's back to normal. Now we'll go to this tab here, the MCMC Setup tab, where we will generate a starting file that we can then download to run the actual Bayesian estimation procedure on our private computer. First things first, we're gonna need to upload our observations. So we click here to upload the observations. And let's get rid of the tooltips. Now they show up everywhere because we restarted the app. Hide tooltips, they're gone. Okay, so let's upload the CSV file. We saved it as observations. And here it is, it's uploaded. All right, let me show you how to actually set the parameters of the Bayesian estimation procedure. If you want to know what the Bayesian estimation procedure actually entails, as usual, you can click here and get the help files. It's going to tell you how to import observations and what format they need to be. We already did that. How to set priors, starting distributions, how to set the proposal distributions, and a rough overview what Bayesian estimations actually are and what's going on mathematically in the background. I mentioned three things: starting distribution, prior distribution, proposal distribution, just very quickly so you know what this actually means. What we do when we run the Bayesian estimation procedure is we guess a set of parameter values, and with those parameter values we run a simulation like the simulation here that we ran before, and then we calculate the probability of obtaining our observations with that simulation, or in other words, we calculate the likelihood. We then also calculate the prior of those parameter values under the prior distribution that we specify. And the product of the prior distribution and the likelihood is proportional to the posterior distribution. Next, we draw a new set of parameter values that is quite close to the old set of values, and we draw them from the proposal distribution. And we run again a simulation, calculate the likelihood with our observations, calculate the prior, and multiply the two, and get again something proportional to the posterior. Now we accept the new set of parameter values or not, depending on the difference between the two posteriors. This is the totally basic MCMC Bayesian approach. Now, in the end, if we do this, we will have sampled from the posterior distribution, and we get an estimate of the posterior distribution of all the parameters. This was just a very brief overview of what we're doing here. As I said, if you need more details how that Bayesian approach works, check out a textbook, YouTube, or the help files here. Something additional, we do not update all parameters together because we work in a Gibbs sampling scheme. That means we change them in blocks. So for example, we change all the motility parameters together, calculate the posterior, and then accept all of them or not. Then we do the same for all growth parameters. You see it here, for all individual level covariates or individual level parameters, and for the parameters determining the initial location. So the spread, the weight, and the actual location. The dispersion or spread, the weight, and the actual location for all locations, of course. This approach helps to improve mixing of the chains because there will be some correlation between the parameters within a group, and with this approach we just have better convergence of our MCMC sampler. As usual, more details in the help file. So now we have a very basic overview of what is going on here, and we can understand what this first MCMC tab does. Lets you set all those parameters of the simulation, the prior, the starting distribution, proposal distribution, some parameters that govern how the simulations are calculated every MCMC step, and then you can download a starting file to your computer that then is inputted in the app that actually runs the estimation procedure. Obviously depends on your system and the size of the grid and so on, or just the system itself, how many steps you actually need to run the MCMC sampler for, how long calculations actually take. But you can already see from the fact that you have to calculate one simulation per MCMC step, and there are 1, 2, 3, 4 blocks maybe to update, and every time you have to recalculate the simulation, it's 4 simulations to get one new sample of the posterior for every parameter. Well, in fact, that was a lie. It's not one simulation. It's one simulation less, because for the individual level covariate, you do not have to run the simulation to get the spatiotemporal effect. You already know that. But anyway, you need to run a couple simulations to get one sample each for each parameter from the posterior distribution. So you probably need to run thousands of simulations, and that will take a long time. That is the reason why you need to download this file here, or why you need to download a starting file and run the estimation on your own computer, because the server here or the app here does not have the capacity, the memory, and so on to actually run this in the app itself. Once you're done, you will be able to upload the results into the app again and analyze it and so on. We'll come to that later. Now first, let's talk about what all these input fields mean and what they're there for. The first group here, that is just to set the parameters of the simulations. Some of them you already know. The scale factor, that's the factor for the homogenization. The type of algorithm, you already know that as well. The time per step. The time per step, before we set it to 1. So our observations were actually generated from a simulation with a time step of 1. But you see that you have multiple options here. They're all fractions of 1. Let's keep it at 1, because that is the time step inherent in the observations. We generated one observation per day. That is also the minimum time step that the app allows for your observations. You could have a larger time step. For example, if there are no two observations that are closer in time than, let's say, 3 days, then the time step inherent in your observations would be 3. Of course, you can run the simulations with a shorter time step. That would mean, for example, when you run it with a time step of 0.5 now, that will mean that only every second step of the simulation can contain observations. You might still want to do that, even though it seems like you throw away half of the steps, because it can make the simulation more exact if you use more steps. However, it would of course not make sense, for example, to use a time step of 0.67. It would only make sense to use a time step that is a fraction of the time step of the data. In our case, a fraction of 1. As you saw, there were some suggestions, 0.5, 0.25, 0.1. It adapts depending on what time step the app detects in your data. We're just going to leave it at 1. This here is something else. This is how many days were there before observation 1, meaning at what time does the app estimate the initial distribution. Should the initial distribution describe the situation 10 days before the first observation in our data file? Should it be 100 days before the first observation? Right now I set it to 1 day before the first observation, which is what happened in the background in the simulation part from which we got the observations, right? We have this starting distribution, and the next step is this one here. So, right, 1 unit of time after the initial distribution, we get this distribution. So I'm going to keep it at 1. So we actually, hopefully, when we run the estimation procedure, get exactly these parameters here back. The final input in this first section of this tab is this block here. And here you can select which blocks of parameter you want to actually optimize or estimate in our Bayesian procedure. You can, for example, give the motility or the growth or any other block of parameters values and keep them completely constant during the estimation procedure and not estimate them at all. For this, you need to uncheck the corresponding entry. All right. Now in this section here, you determine the prior and starting distributions. Well, you know what? Let me uncheck this here, so we do not estimate the initial locations, only the dispersion and the weight. This will just make it run faster, converge faster, and make everything a bit easier. So now back to setting the prior and starting distributions. Let's first do it for the motility and growth parameters. We're going to set the starting distribution, or the mean of the starting distribution. When you start the simulation or the estimation, we need to guess first parameter values. So we need to have an initial guess of parameter values. Since we will run multiple MC-MC chains in parallel, we need a guess for all parameter values for each chain. Each chain will start with a different set of parameter value. So we introduce a Gaussian distribution with a mean and a standard deviation. And from that Gaussian distribution, one for each parameter, we'll draw a parameter value, and we will start the chains with draws from those Gaussian distributions. So first, let's set the mean, and we can set it for the motility and the growth parameters. Right now, they're all at 0. For example, we could say we want to draw the initial values of the intercept parameter from a normal distribution with a mean of 2. Obviously, we know the true values of the parameters. So to make everything a bit easier, and in real life, obviously you couldn't do that, but to make everything a bit easier, I'll just enter here the true values. So we'll have a distribution. We're gonna enter a standard deviation as well, but the parameter initial parameter values will be drawn from a distribution centered at the actual true parameter values. For this, there's the import values button. You can click it, and that just imports all the values from the parameters tab. You can compare it, intercept -1, continuous covariate 0.4, intercept -1, continuous covariate 0.4. So we just imported all those parameters from the parameter tab as the mean of the starting distribution. You see it here in the table. For the motility parameters, the mean of the starting distribution for the motility, the mean of the starting distribution for the growth. The standard deviations are still all 0. We have not set them yet. The transferring of the parameters is not only useful when you actually know the parameters, because normally you don't, but you might just want to play around with different parameter values, run simulations, see what the effect is, and so on. And once you found a set of parameter values that you're happy with, you can keep them here and then just import them as parameters or as the mean of the starting distribution. We're just going to set the standard deviation to quite a small value. Let's just set it to 0.1 for every parameter. And we were not going to estimate the interactions. Let's just leave the interactions. We know they're 0. Let's just leave them. And because we leave them, we can click Fix. So we want to fix them at 0. They're not estimated. All right, so now they're fixed and they won't be estimated. They're grayed out. Good. And you don't have to do that in the starting standard deviation modal window. You can do that when you set the mean. Here they're listed as fixed as well. Or when you set the prior, here they're listed as fixed as well. You can click anywhere on fixed and it will fix it for all. Actually, that is what we need to set next, the prior. So now we need to set the mean of the prior and the standard deviation of the prior. It's again a normal distribution. In simple terms, the prior represents our initial knowledge of the system. Once again, we could go to the parameters tab and play around with some parameter values, run the simulation and so on, and see between what limits of parameters the simulation still makes sense or still kind of represents the reality that we think it should. Once again, in our case, we know what the true parameter values are, so let's just set the prior mean to the true parameter values. Done that by clicking Import Values. Next, we need to set the the standard deviation of the prior. It's all 0. We're not just going to set it to 0.1, but we're actually going to play around a bit with parameter values, run a simulation, and see what that does to the simulation. Let's change the parameters just a little bit. For example, let's make the intercept a bit smaller. Make that also smaller. Let's make that larger. Let's make that smaller. And the same here. All right, we made some of them smaller, made some of them larger. Let's see how the motility rate has changed and the growth rate. Okay, a bit different. Let's just run the simulation to see what happens. Okay, looks a bit different. Maybe for some reason we believe that this kind of represents the entire parameter space, or that we have initial knowledge of the parameter space, and this is kind of the limit. Okay, so we want to somehow represent this with a prior distribution. So what we can do is use those values, or set the standard deviation of the prior, so those values are the 95% quantile or the 5% quantile, depending on whether they're smaller or larger than the mean of the prior. Let's go back to tab here, go to prior standard deviation, and we just click import 5%, 95% values, and that's what we got. So we have now standard deviations that are chosen, so the values we have in the parameter tab are the 5% or 95% quantile values of the prior distribution. Done. Here they are. So we have a starting distribution and a prior distribution for the motility and the growth parameters. By the way, if you want to fix a parameter, you don't only have the option to fix them at 0 as we did with the interactions. You could also say, I don't want to optimize, or I don't want to estimate the intercept. I know it is 1. So you can go here, say fix intercept of the motility, for example. And now it is not fitted and it is fixed to 1. Let's undo that. We said 0.1, and for the prior, well, we can just do this again. And there we are. Now we need to set the parameters for the individual level covariates. Let's open this here, and there is just one individual level covariate from our data. If you had more of them here, they would be listed here together with their parameters. You'd have the interactions as well. Or if you had factors, you'd have dummy variables here, and so on and so on. We took it a bit, we made it a bit simpler and just have one covariate. Let's give this a value of 1. And as usual, the starting standard deviation, let's give it 0.2, whatever. And prior mean, 1. Prior standard deviation, 0.5. You saw that you also had the option to import values. Now you might ask, in the parameters tab, there's only one beta parameter. What happens when we have multiple covariates here with multiple parameters? Now that we've uploaded an observation, a new distribution is available called the empirical distribution. So when you click it, this then, instead of drawing individual level covariates from a normal distribution, it draws them from the empirical distribution of the individual level covariate as it was obtained from the data. Meaning it just fits a kernel density estimate of the data of the individual level covariates, plural. In our case, we only have one, so when we click enter beta here, there's just one beta parameter. But if we have multiple individual level covariates in our observation file, you'd have multiple beta parameters here. And you can generate observations with those beta parameters from the empirical distributions of the individual level covariates. And when you have a value for each beta parameter here, you can then import them here. This is why the import values is there for the individual level parameters as well. Last thing, the initial location parameters. Let's start again with a starting distribution. Note that the initial location point, so the x and y position of the initial location, is already set to fixed. Why? Because we deselected fitting it here. We said we do not want to fit any initial location, so that's actually the same thing as setting every initial location to fixed by hand. We know that we have two initial locations, so we should add another one here. And fix that as well. So we added another initial location. We can also remove initial locations. Now we only estimate one. The number of initial locations you cannot estimate. The app is not capable of doing that. If you you're not sure how many initial locations you have or how many locations of introductions there are, the only thing you can do is run multiple estimations with different numbers of locations of introduction and then compare the results. So right now we can import values again and import values from the starting tab because as usual we know the true values. So let's import them and let's fix them again. This was unchecked because we imported new values. We have the two starting locations with the X and Y values. We have the initial spread and the initial scale. Instead of specifying a mean and a standard deviation separately for the X and Y position of an initial location, you could instead upload a probability density function, and the initial location will be then drawn from that two-dimensional probability density function. To do that, you can click here, and now you can upload two rasters, meaning an RDS file containing a raster or a TIFF file and so on. And obviously this does not have to be a normal distribution as it has to when you upload it or when you generate the starting distribution like this with a mean and a standard deviation. When you upload a raster, it can be any probability density function. To actually upload it, click here, and I've prepared one. It's called prior location raster 1, and you got prior location raster number 2. One is an RDS, one is a TIFF. Doesn't matter. Now it says raster uploaded, and you cannot specify a mean anymore. Same, of course, with the standard deviation. You cannot do that. You can do exactly the same thing for the prior as well. That's just a warning that doesn't matter because we cannot have a spread of 0 for technical reasons. It has to be larger than 0, a bit larger. We're actually not estimating the initial location at all, so we can remove the rasters we uploaded again and set it to fixed. So let's remove them. They're gone. And we set it to fix again. We could have, by the way, uploaded it just for one and specify the other with a mean and a standard deviation. This can be combined in any way you wish. Let's remove it again. All right. Need to specify the standard deviation. Let's set it to a value of 0. Well, no, actually, let's set it to a value of 1 for both, and let's set it to 0.1 for the scale. For the prior, import it again, import values. So we set the mean of the prior to the true values. Because we did that, it deselected the fixing. So let's deselect it here, no fitting, meaning it is fixed. The initial location is not estimated. Finally, the prior standard deviation. Let's do the same thing as with the other parameters. Let's play around a bit with the starting distribution. Maybe increase the dispersion a bit of that one. Maybe increase the dispersion a bit of that one. Play around with the weights as well. All right, and maybe we're happy with that being the 95% quantile of dispersion and weight, of the prior distribution of dispersion and weight. So let's go back here and say import 95% quantile, and we have standard deviations so that this is actually the 95% quantile. Good, so we're done with those parameters. Now down here, we need to set the proposal distribution. Every step of the MCMC sampler, a new set of parameters is proposed. This new set of parameters is drawn from a normal distribution again. The mean of the normal distribution is the previous value of the parameter, the old value of the parameter. What we can specify is the standard deviation. So how far are the jumps, quote unquote, of the parameters that we make when we suggest a new parameter value. All jumps are set to 0.1 at the moment, and I think we're just gonna leave it at that. The ones that are grayed out are the ones that are fixed. I think we're gonna leave it at 0.1. We don't have to be very specific here because we have the option to continuously adapt the standard deviations of the proposal distributions during the MCMC runs, during the Bayesian estimation. You specify this here. So this says after every 10 MCMC steps, the standard deviations of the proposal distributions are readjusted. And they are readjusted so that the acceptance ratio goes towards this number here, towards 30% is what we have at the moment. So the target is that out of the 10 steps that we make before we readjust the jumps again, 3 of them are accepted. This is, by the way, a reasonable number for a higher dimensional problem, so an estimation with multiple parameters. By the way, the proposal distributions, so the jumps, that does not really matter for the result, or actually it does not matter at all for the results. It just matters for the convergence. So the better you choose your proposal distributions, the quicker everything will converge. If the proposal distributions are too wide, you make too big jumps and you end up rejecting a lot of proposals. If the proposal distribution is too narrow, you stay basically very close to the previous parameter value and you don't reject, but you do not explore the hyperspace, the parameter space very well. Finally, you don't have to update the proposal distribution for every parameter. You can select for which ones you want to do that. Right now, initial location is selected, but we don't even estimate the initial location. You don't have to worry about that. The code will do that itself. Okay, so now we're done. We set parameters for the simulations. We specified what we actually want to estimate. We set the prior distributions, the starting distributions. We set the proposal distributions. We can check the parameters one last time. Utility, growth, individual, location parameters. Looks all good. So now we can download a starting file that we will then feed into an app on your local computer that will run the Bayesian estimation procedure. If you don't have the code in your computer yet, so you can't run the estimation, click here to download the full bundle, meaning the starting file and all the installation files to run the code on your computer. Save it. It's a zip file, so you need to unzip it. Okay, so now that it's downloaded, let's get out of here and let's save all these parameter values. So once again, we'll go here and save the current state, all those parameter values, all the covariates and so on. Save current state, and we'll call it MCMC param save. All right, so now we can safely close the app and I'll show you how to run the Bayesian estimation on your computer. I unzip the folder and this is what you get. If you're on Windows, you can just double click Setup and Run. And that will do the following. It will check if you have R installed, and if you don't have it installed or have a version installed that is too old, it will download and install R for you. Then it will install all the packages you need. It will install a C++ compiler that you will need because a lot of the code is in C++. And it will then start the app where you can run the Bayesian estimation procedure. If you're on Mac, this will not work. Maybe for some other reason, for some settings of your operating system, it doesn't work either. Anyway, should it not work, all the code is in this folder, code. And what you need to run is app.r. This is the main app that you need to run. If you need to do stuff by hand, you need to install R by hand, need to install all the packages by hand, and a C++ compiler. But once you've done that, open app and run the code in it. Or, since I'm on Windows, I can just do this, double click setup and run, and say run. Your computer's going to warn you that there is no virus promised. I have R installed. It's just verifying some stuff, loading libraries. All right, the first thing we need to do is upload the start file that will contain all parameters, all the data, and so on that we need to actually run the estimation. The start file that we produced with the main app. You can upload it here. It was called start. And now from top to bottom, we can set the following things. We can set how many MCMC chains we want to run. There's going to be one chain per CPU. So this depends on how many CPUs your computer has available. If you have, for example, 8 CPUs, here's a pro tip. Don't actually use 8, otherwise you don't have any CPUs left to use your computer. It detects how many CPUs you have available and already puts here a good number, a good upper limit. I'm going to use 11. Next, we can specify for how many steps we want to run the MCMC sampler. You don't know a priori for how long you're going to have to run it until you achieve convergence, but you can always restart it. Let's put here a reasonable number, let's say 5,000 steps. Okay. Now I already said it, printing of the restart files. Now every 10 steps a restart file is written. That means if it crashes in between, you only lose a maximum of 10 steps. But those are a lot of restart files. If you run it for 5,000 steps, and writing a restart file to disk takes quite a long time. So I'm gonna set this to 2,500. So there's gonna be only one restart file written. You see it here, by the way, in the progress bar. This is the progress bar that will increase while running the estimation. And the red line is where a restart file is written. There is just one restart file in between, and then the final restart file, if you will, which is the results file. We can do thinning to already reduce correlation a bit. Thinning just means you delete every nth step, in this case, every second step. Those are all the settings that you can do here, and now it's just time to run it. The only thing I forgot is you can uncheck this and it doesn't show the save points anymore. Doesn't really matter. All right, let's run it. This is going to take a few seconds before it actually really starts the calculations, because it has to set up a parallel environment with the 11 CPUs, load all the libraries onto each CPU, and so on and so on. So this might take a second. We're just going to wait here. While it is running, if you want to cancel it, you can always click the cancel button and that will stop the calculations. Now it started, we're at 1%. If you want to have a bit of more detailed overview, you can do this, show individual progress bars, and you will see one progress bar per CPU. Also, you will see how many steps are already calculated. We're at 265 steps out of 5,000. After 2,500 steps, remember, there will be a restart file written. That will take also maybe 30 seconds in that ballpark. And then it continues with the estimation procedure with the MCMC steps. I'm gonna skip ahead here. Okay, about 4 minutes have passed, 3 minutes have passed, and now we've reached the point where we're gonna write out a restart file. We're at 50%. So it's time to write out a restart file. The code will inform you about that, but like I said, it will take about 30 seconds or so to write the restart file, and then it will continue running. And we're running again. Look at the individual progress bars. All right, so we're at the end. The final restart file has been written, which is actually the result file. And we're done. Now we can take the last restart file and upload it into our original main app. We could have done that while the estimation was still running. We could have uploaded a previous restart file, checked on the progress, and so on. In fact, we could also, of course, and that is what a restart file is there for, upload a restart file and continue running it. We're back in the main app in its default state right after startup. And now we can go into the MCMC extract tab and get rid of the tooltips and upload a restart file. I stored it in a folder called restarts, in that folder where we ran the estimation. And let's open the second one because that is the final restart file. Okay, so you see in this table every parameter that was estimated. You see the median of the posterior distribution of that parameter and the 95% credible interval of that parameter, of the posterior distribution of that parameter, and a selected value. I'll come back into that in a second, what the selected value is. Right now, it's equal to the mean. Good. You can click on any of those parameters. Let's click on the diffusion intercept, and it will show a plot. In this case, the trace plot. So you can analyze convergence of all the chains. Apparently this was a very bad starting location in that chain here. There was no steps were accepted for a long time, and then finally it moved out of that region. So you can check convergence here with the trace plot. Obviously you can switch parameters, look at all the different parameters, how the convergence looks like. Of course, when you look at the location parameters, the x-coordinate and the y-coordinate of the initial locations, nothing happens here because we fixed them. A constant for all chains. The trace plot is not the only thing you can look at. You have the autocorrelation plot. You have the density. So this is a kernel density estimate of the posterior distributions from the individual chains. So you can see how well they overlap, if there's multimodal distributions, and so on and so on. By the way, this is not converged, and this is not a really good estimate, and so on. This is just for demonstrations. You can look at the running mean of all the chains for the different parameters. And of course you can, well, let's first look at the jumps. So how the jumps were adapted. It restarts at 0.1 when you restart the estimation. So when you write out a restart file and restart it from it, it starts with the original jump size, which was 0.1. This kind of gives it another boost. And finally, you can plot the posterior distribution. Oh, and by the way, no, before we plot the posterior distribution, let's quickly look at the trace plot again. And see what this does here. You can designate a certain number of steps as burn-in. For example, the first 1,000 steps. So you see it has adapted the table. The medians have changed. The 95% credible intervals have changed. And of course, the plot has changed. It now only goes from 0 to 1,500 because we dropped 1,000 steps. By the way, I forgot to mention that below the plot, there's the effective sample size and the Gelman-Rubin statistic to assess convergence. If you want to know what that is, as usual, check out the help files. Okay, so the final plot that we need to look at is the posterior plot. So this plots the posterior density of the selected parameter. You see the median, and the 95% credible intervals. You can click anywhere on the plot, and this will select a value. It is now here in the table under selected value. See if I click on a different part of the plot. This is now the value. Okay, I can do that for every plot separately. Select different values, or I can click set to median, and that sets the selected value of every parameter to the median of that parameter. Or final option, I could click draw from post, and it just randomly draws a value from the posterior distribution. Okay, why do I do this? This is the value that I can then transfer to the parameters tab. So I can draw a random value from the posterior distribution or select the mean, whatever. Anyway, whatever I have selected, I can then press transfer, and that puts those parameter values into the parameter tab, into the starting value tab when it comes to the x and y coordinates of the starting location and the dispersal and the scale of the starting distribution. And be careful with that because it also transfers or puts in the covariates that were used to estimate those parameters. So every covariate that you have here is overwritten. We don't have any covariates at the moment, so we don't worry about that, but there is a warning to tell you about this. So now we press confirm. And you see those are the covariates with which we estimated the parameters. Those look familiar. This is, we use the median of the posterior, by the way. Looks very similar to the parameters that we started with. And same for the motility rate, growth rate. Those are the medians of the parameter values. And like I said, kind of similar to what we started with, which is not surprising because we used quite a tight prior, even though we ran the MCMC sampler for only a few steps. In this way, you can basically explore the posterior predictive distribution. You select values from the posterior distributions or draw values from the posterior distributions, transfer them to the parameters tab, and run simulations. And from those simulations, you can, if you want, generate observations again. In a real-world setting, you could now, for example, change covariates or add covariates and see what influence that has on the spread of a disease or whatever you're analyzing. Or you could, for example, further predict the spread of the disease by just increasing the number of steps for which you run the simulation here. And when you've done that for multiple sets of covariates or different covariate values and setups, you can then, you already know this, come to the analysis tabs and compare and analyze simulations.